All right, so we are going to go through example 1.61. So first we'll just read it. A solar flux of 700 watts per meter squared is incident on a flat plate solar collector used to heat water. The area of the collector is 3 meters squared and 90% of the solar radiation passes through the cover glass and is absorbed by the absorber plate. The remaining 10% is reflected away from the collector. Water flows through the two passages on the backside of the absorber plate and is heated from an inlet temperature Ti to an outlet temperature To. The cover glass, operating at a temperature of 30 degrees C, has an emissivity of 0.94 and experiences radiation exchange with the sky at negative 10 degrees Celsius. The convection coefficient between the cover glass and the ambient air is 25 degrees Celsius. At 25 degrees Celsius is 10 watts per meter squared Kelvin. And then we have just like a little image, and then just the actual problem. So for A, perform an overall energy balance on the collector to obtain an expression for the rate at which useful heat is collected per unit of the collector, Q, like the heat flux U, determine the value of heat flux U. Calculate the temperature rise of the water, T0 minus T inner, if the flow rate is 0.01 kilogram per second. Assume the specific heat of the water is to be 4,179 joules per kilogram Kelvin. And then part C is the collector efficiency is defined as the ratio of the useful heat collected to the rate at which solar energy is incident on the collector. What is the value? Okay, so that was quite a bit. So we're just going to start off easy. We're just going to start off with the knowns. Okay, so we know that just Q from the sun equals 700 watts per meter squared. The area equals 3 meters squared. We know that 90% of the solar flux is absorbed. We know T glass equals 30 degrees Celsius with an efficiency of 0.94. We know T sky equals negative 10 degrees Celsius, and H equals 10 watts per meter squared Kelvin. Okay, so just to give you guys just a little picture, because when I first was looking at this problem, I was also just like a little confused. Totally chill if you guys are confused as well. So we have our image very similar to this. I just am going to draw kind of like the control volume around. So we have Q solar coming in. We have Q radiation going out. We have Q convection going out. And I'm going to kind of draw it in the middle. It's these little tubes of water. It's going into the tubes of water is how I'm interpreting it. But that's what that QU is, or the like the useful heat collected. It's collected kind of like in the water, but it's like not staying within it. So that's that QU, but that's kind of going out, but like not to the air. And then just kind of like to give yourself just like another kind of picture of what this is looking like. That's a heart. Those are those water tubes. Again, we have the control volume kind of going around here. We have air over here, which T infinity equals 25 degrees Celsius. H equals 10 watts per meter squared Kelvin. On the surface, we have area equals 3 meters squared. T glass equals 30 degrees Celsius with an efficiency of 0.94. And then over out here, we have T sky equals negative 10 degrees Celsius, as well as we have a sun and that is giving off QS, which equals 700 watts per meter squared. And just note that QS is different than Q solar, which we'll kind of go into in a little bit later. And then we have water in here, where we have T in, T out. So that'd be like the temperature of the water as it comes into this little unit and the temperature out as it comes out. And it's flowing at 0.01 kilograms per second. So I think just like the combination of these two images makes it a little bit easier to understand. Now to go into some assumptions. We're going to assume steady state. We will assume no heat loss. So the sides and back of this, we're just going to assume that it's well insulated. There's no heat loss out of this collector. And then we're going to also assume the collector is small compared to the surroundings. So now that we have our assumptions, we have all of our figures, we can kind of get into the analysis bit of it. So I'm gonna go down here. So we have part A. So we're doing an energy balance. So we have E in minus E out plus E generated equals. So these are both zero. There's nothing stored. Any stored energy is going straight to that water. I guess it's not stored at all. It's just going out. It's going straight in and out. So then when you add up all the arrows, you have Q solar minus Q radiation minus Q convection minus QU, which is what we saw before, equals 0. Just a little side note, Q solar equals that 0.9 or 90% efficiency times that QS. So that'll equal 0.9 times 700 watts per meter squared, which equals 630 watts per meter squared. So if you take this equation and rearrange it and plug things in, you get QU, which I just brought this over to the other side, equals, again, that 630 watts per meter squared watts per meter squared, sorry, minus your efficiency times the Stefan-Boltzmann constant. We have T glass to the fourth minus T sky to the fourth. And then we have minus H T glass minus T infinity. So I'm just going to plug everything in. 630 watts per meter squared minus the 0.94 times 5.67 times 10 to the negative. Oops, that kind of looks messy. 10 to the negative fifth watts per meter squared Kelvin to the fourth. And that'll cancel out our Kelvin to the fourth. So for this, the T glass and T sky do need to be in Kelvin. With the T glass minus T infinity here in the convection, we don't need to convert to Kelvin because the difference between Kelvin and difference between Celsius is the same. But because for here we have this T to the fourth, you have to actually convert it to Kelvin to get like the proper calculations. So that is 303 Kelvin to the fourth minus 263 Kelvin to the fourth. Just gonna kind of continue on to the next line. Minus 10 watts per meter squared Kelvin times 30 degrees Celsius minus 25 degrees Celsius. So that is like the full equation right there. And then when you go and plug it into a calculation, you get 386 watts per meter squared. So for B, if you guys remember, we want to calculate the temperature rise of the water, T outer minus T inner, or sorry, T out minus T in. So we are going to use this equation. We have QU. We're going to move it so it's not heat flux anymore. And then we have our mass flow rate, we have CP, and then we have T outer minus T inner. So then when you rearrange this, you get T out minus T in equals U over A, M dot CP. You can plug those all in. Area, if you remember, is 3 meters squared. All over 0.01 kilogram per second times 4,179 joules per kilogram. And you get T minus T inner equals 27.7 degrees Celsius. And then lastly, C, we need that efficiency, which will be the heat flux, like they described, the ratio of the useful heat collected to the rate of the solar energy. So that was that QU over QS. We're not going to be using the Q solar that we calculated up here, right here. So this is of the total QS, so not multiplied by that 0.9. So then you would do 386 watts per meter squared over 700 watts per meter squared, and that equals 0.55 or 55%. And that is the end of this problem. I'll just leave this up on the screen for a second, just so you guys can copy down anything that you are missing. Thank you.